Yeah, it's okay. I have no idea how this is going to work, but let's see what happens. Um, spin. Okay, cool. Let's see, and then hide building controls. Cool. So now this should work properly. Oh, cool. Oh. Cool. Hello. Hi. Should we? I guess those lights are already off. Can everyone see this all right? Bet. Okay, cool. Hi. Welcome to a very informal presentation on quantum simulation. So first off, I feel like quantum simulation is like one of the cooler things in quantum computing. Like at least it's the whole reason I'm doing this. And like, so it's also a big part of my research. So that's why we're talking about it. But yeah, so yeah, quantum simulation is kind of fun. And it's going to be also, I'd argue, one of the most like weird killer apps in a quantum computer, because it's going to be basically allowing us to do stuff we've never really done before in a very visceral way. Okay, like molecules and stuff. And so yeah, let's move on. By the way, trivia. Who knows what movie this is? Ronnie points for trivia. Nah, it is Korean. It's Burning. Yeah, but anyways, that is not the point. So yeah, so basically today, here's a rough outline of what we'll be doing. We'll be going over some motivation, some of the pipeline that you'll see for quantum simulation, how to make, I guess, matter slash energy into Hamiltonians. We'll tell a story of the awful scaling, and then demo at the end with some of the research I'm doing right now. It's not actual research. It's like what we'll be demoing is like all the stuff I had to make so that my research is like can be done. So anyways, so yeah, cool. So let's start with motivation. So the main thing with motivation with this stuff is basically the fact that we already kind of know all the physics. So here's a great quote by Dirac. It basically is the TLDR of it is basically that we already know like basically everything we need to know about simulating like chemistry and particles and all this. But the only issue is that Hilbert space is a big place. These quantum systems have a massive amount of entries in them, which is going to be making it basically makes it computationally feasible on like computers that we have right now to do this stuff. Okay, so yeah, just if you just remember our main motivation, the mantra should be Hilbert space is a big place. Okay. And so yeah, I wanted to also, because I figured you guys are interested in this stuff too, hence why you're here. What are some potential applications of like quantum simulation that people can think of? I just wanted to list them out. Finance. Okay, that's lame. I caught the quant guys. Let's see. Yeah, drugs like medicine. Yeah. Yeah, so these are just some of the like the many things that we'll be able to use with them. And think about it like this. These are like just the ideas we have now without having the technology. And so I don't know if you guys feel this way, but like I always feel like when technology actually happens, we finally see its use. And so so quantum computers are obviously the most prime example of that right now, where we're starting to make them and we have some ideas, but we really don't know what they could lead to. But hopefully some cool things. Like personally, I'm not really interested in any of these. I just was like, you know what? I just want to like simulate like a chair with all of its atoms in it, you know? Like I was always like, when I did 3D graphics, I was like, why don't we just like put all the atoms in the chair and make the chair that way? And I realized, oh, it's because Hilbert space is a big place. So this is the same sort of idea. You can that we're basically just like going to take these matter and simulate it on a quantum computer. Okay. So basically, this is the pipeline that we're going to be using. We kind of ignore this because I'm not an error correcting person, so I'm not going to deal with that. But we are going to deal with is basically identify some systems Hamiltonian, encode that Hamiltonian in some way into qubits, and then do a state preparation and some like state evolution. Okay. These second, so we will mainly be talking about this and this, and then we'll be demoing this and this, but not in like we'll be doing demoing it in my research, which is a different way than it actually lists out here. It's using a variational algorithm, okay? So yeah, any questions before I move on? Nope. Cool. All right, so let's get into it. All right, so basically this is the like kind of pipeline you see for like translating specifically matter into qubits. So we'll be actually going over two examples. We'll be going over a matter example and then like a particle field theory example. But like with molecules, you can like kind of form them into a Hamiltonian, and then what you can do is you can make that Hamiltonian into qubits. And this is, by the way, courtesy of Jared R. McLean, who is a big part of my research because literally two of his papers on VQE and barren plateaus are like the seminal papers in what I do research on right now. So very useful. But regardless, let's get into that translation. So I just want to actually point out here actually has some of the more important parts. So like these are just like a bunch of like a smorgasbord of ways that we can do this depending on the system that we have. So those of you taking quantum mechanics, you may have heard of fermionic and bosonic Hamiltonians and things like that. And basically these have like mapping. So fermionic is Jordan Wigner, bosonic is Brevi Kitaev, and things like that. So, but we're not going to go too much into that. Just know that there are like predisposed methods that you can use depending on your Hamiltonian to translate it into something that makes sense to qubits. Okay. And so for hydrogen gas, this is what it looks like. So remember, this is like hydrogen else is H2. So at least according to Kiskett, this is like a version of the hydrogen gas Hamiltonian. And so basically what you have here is poly strings. So these right here are poly strings. So these are just like your standard like I, Z, X, Y. And then what you're going to do with them is you're going to tensor them all together, okay? And so this one is a 2-qubit Hamiltonian. And basically it's going to be the sum of all of these particular Hamiltonians, and then sum together makes the big Hamiltonian. And you can see that Hamiltonian here, okay? And we'll actually be going through a simulation of this Hamiltonian later. But yeah, so any questions at this point? Yeah. Yeah, I don't know. I just pulled the lock Qiskit. Yeah. So I don't they don't need to add up to one, I think, because because this isn't going to be unitary. This is the Hamiltonian. When we translate it into a unitary, it's going to still have its order preserved, sorry, magnitude preserved. But Hamiltonian doesn't need to have magnitude one. But we'll go into exactly how that is. So yeah. So basically, this Hamiltonian, so again, for those who may have taken quantum mechanics, it's going to tell us like basically the energy of the system, right? And so the main things we want is like, so we have our energy function, awesome. So now what we want to find is like the eigenvalues, because that corresponds to the energy. And then specifically, we really want the lowest eigenvalue, which is the ground state, because basically, the intuition behind that is that we can use that ground state to predict like our system at low temperatures. Ground state is where most of our quantum effects kick in and such. So ground state is going to be a really important thing. And in the demo later, we're going to basically just be looking at the ground state of the system. Okay. So yeah. Yeah, it's, I think it's quite nice. So this is just like basically our problem statement now. And now everything we're doing is going to be about finding eigenvalues, okay? And as you know, that is a surprisingly hard thing for matrices bigger than like this. So let's go into the first thing about this that's weird. Horrible scaling. So this is another example of a Hamiltonian. So this is the Schwinger model. So this is what I do research on primarily. And basically what it is that it's like this is a qubitized example of a quantum electrodynamics model, which is described as one spatial and one time. And basically this n here that defines the like size of the model is basically just saying, given some volume of like basically interactions of like electromagnetism in well, quantum electromagnetism, we're going to discretize this model at a certain number of points. That's going to be n points, okay? Yeah, don't take this model too literally though, because it is like by conception a toy model, okay? So it's like this is like probably one of the simplest quantum electrodynamics models, and it's, as you can see, it already has all these weird combinatorics going on. Okay, so yeah, now that we've started to go through that, like let's see the horrible scaling that we'll be encountering. So yeah, basically the Hilbert space is a big place. So for the endpoints in our model, this is going to be like this amount of numbers in the Hamiltonian, right? Because it's just going to be like 2 to the n times 2 to the n makes our matrix, and then that's how many entries we have. And it is absolutely awful, the scaling, because it's literally 2 to the 2n. And so at 2, you have 16 entries. At 6 points, you have 4,096. At a measly 134 points, you already have more like entries than there are particles in the universe, okay? So it is quite awful scaling, okay? For a classical computer, right? Because like we know matrix multiplication in a classical computer, you have to like store the bits of like every digit and then like do the multiplications and additions, everything. So it is awful how bad this is, okay? So yeah, any questions up till this point about this? Or I guess I anticipate questions about this because this is a little complex. Yeah. Oh, so that's like a summation. So like so so the notation here is kind of weird, but basically n is going to be like the size of the Pauli string. So it's like, for example, one size, so if like n, so for n equal to 6, you can have like x, x, I, y, y, something like that. And that's like the size of the Pauli string. Okay. Cool. So yeah. Yeah. Any other questions? Yeah. Yeah, exactly. Yeah. So that's like the other reason, because it's like, well, you want a linear number of particles, so I want a linear number of computation for that. But regardless, yeah. But great questions. Let's move on to the next part. So yeah. Now, luckily, the thing is, as we know with quantum computers, like, you know, just like having like that x is like literally just like we can have like a bunch of lines, and then it's just like, oh yeah, here's our x, here's our line, kind of thing. So it's literally the idea here is basically that this value n, which you can think of as like number of points on a lattice or number of qubits, what have you, that we want to that we scale linearly to like figure out what is going on. For a quantum computer, we have n qubits that's going to about n qubits that's just going to maintain. So basically, the main point here is that classical, it scales these systems exponentially, but quantum computers can scale these systems polynomially. Okay, so that's like the kind of the punchline. So yeah, any questions? Nope. Okay, cool. Let's move on. All right. So yeah, let's talk about prepping the state. So we're going to be diverging from this model a little, because this model is like from a paper I saw about like quantum simulation on superconducting qubits by IBM. And yeah, so they do it this way because it's more exact, and it's like, this is the way we want the future to be. But what I'm going to show you right now is a variational method that is more likely to work on like computers that will be quantum computers that we see in the, hopefully, you know, the next 5-10 years, hopefully. So yeah, let's look at that. So yeah. So actually, have we talked about VQE in this at all yet? Okay, cool. I'll just like briefly touch on it a little more now. And we'll see an example of actually VQE. So the VQE is basically this like method of evaluating the energy eigenvalues of some Hamiltonian, okay? So how you read this is basically you start here and you have some Hamiltonian, and then you choose an ansatz. And ansatz is just a fancy name for like a circuit. So you want the circuit to vaguely be like relative to your Hamiltonian, and we'll see a very little example of that soon. And then what you're going to do is this ansatz is going to be like parameterized by a bunch of parameters in this theta, okay? And so basically what you're going to do is that you're going to plug all these in, make your ansatz, make your parameters, plug them all in, and then you're going to evaluate your Hamiltonian at the wave function that this quantum circuit gives you. And I'll explain more of that later. And so basically, once you have this, you're like, okay, how good was that? Oh, it's not very good. Okay, let's shift these values some more. And then we shift them again, and it's like, oh, okay, cool. Did that give us better energy here? It's like, yes, that did. Let's keep on going that way. And so it's a very literal energy optimization. We'll actually see a landscape of this later that shows it more visually, but for now, just like think that basically VQE is like a way of finding energy eigenvalues through iteration of all different of just trying random values. Okay, so yeah, so this is like an example of like an ansatz that we'd see in VQE. So here we're H2 back to our Hamiltonian, and so this is like this state that we're preparing to evaluate the Hamiltonian. And so this is I'm just gonna like throw out some lingo. Don't worry if you don't know it. I'm just saying it for posterity, but basically this is a QAOA ansatz. And what we're doing is we're separating all of the z's in our Hamiltonian from all the x's and y's. And then so we're putting all the diagonal terms because, you know, z is like 1, -1, and I is like 1, 1. So we're having all the diagonal terms in this one and all the other terms in this other. Okay. And so basically, this is going to be called the driver, and this is called the mixer. And so this is what I mean by parameterization. We're going to take these Hamiltonians, exponentiate them with some phase I and their gamma. And just remember, I don't know if we proved this at all, but basically, with the Hamiltonian, you can make a unitary out of it by taking its exponential ci, and this is how you get the normalization. Okay, so yeah. Basically, this is like a very rough outline of what VQE does. Do I have any questions about this? Nope. Okay. So yeah, you might be wondering, so yeah, this remember this wave function here is what we're going to be evaluating h at, okay? And then yeah, we're tuning these parameters. So yeah, and then I just want to like give a little intuition for why we care about this and why it's like noisy. It's okay to be noisy and this is still good. It's because we're going to be evaluating this like a bunch of times. And so maybe you've seen the histograms that like Qiskit creates when you create when you like measure something, but basically that's the exact histogram that we're going to get here. And so this histogram is going to tell us what our wave function is, and then we're going to be able to evaluate the wave function at h. That's like the heuristic sense. There's a lot more details that like makes this weird, but this is like the main idea. It's that you're basically able to measure the circuit a bunch of times to get a pretty good probability distribution that is hopefully going to be somewhat independent of the amount of noise you have, because the law of large numbers, even if you have noise, it's going to converge to some value. And so once you do that, you have our wave function and we can start to evaluate stuff. All right. So any questions about this so far before we go into demo? Yeah. Yeah. That's well, for what I do, yeah. Yeah, you're only trying to find the ground state energy. Yeah. Oh, that's for like the quantum chemists building to take care of. Yeah. So I only know about like the why we get the low energy eigenvalues is because like that's like low thermal at low temperatures we get the interactions are going to be of low eigen close to the ground state, and then also just like the usually quantum effects are going to be at low eigenstates because you know more energy, more likelihood of measurements and things like that if wave function swaps. So so the ground state is usually actually one of the hardest things to get like in a lab. So yeah, cool. So yeah, let's go into demo because that'll be fun. So let's see, where is my demo? Cool. Awesome. So yeah, basically I'm going to do a simulation of hydrogen atom and Schwinger model here, okay? So this is just some code. I'll walk us through like what this code says. So basically this is like making the hydrogen gas Hamiltonian. So I like have defined this. And then basically, as you can see, this is our like target. Target Hamiltonian is like the Hamiltonian we're trying to evaluate. And then the driver and the mixer are like here. So like here's the driver right here, and here's the mixer right here. All right. So this is again one of the intuitions for why the state is useful is because, well, we're literally just making a eigenstate based on not an eigenstate, just a quantum state that is rooted from the original Hamiltonian. Okay. So yeah. So basically, but hopefully this gives a good picture of like driver, mixer, targets. So yeah, we have prepared our wave function. Awesome. And also note that this is like size 2, so this is only 2 qubits. Okay. Cool. So now we're solving a matrix. So I went ahead and just like calculated because this is a small matrix, so like any classical computer should be able to do this fine. And so the eigenvalue of this matrix is like negative, the lowest eigenvalue is like negative 1.85, and this is what the matrix looks like again. Okay. So now let's actually run the circuit and find its values. So this is just like a algorithm program I wrote, and here is the wave function. So this is like that psi theta thing that we saw earlier. This is it parameterized. It's kind of small, but basically it's what you kind of see here is like you see like gammas and betas. So those gammas and betas are the things we're like tuning to get like good values. Okay. And so what we can do, luckily, because this is like only 2-dimensional, so 1 gamma, 1 beta, and so it's very small, is that I can actually show you a plot of it. So this is like the energy that you get from evaluating the Hamiltonian at various gammas and betas. Okay. And this is like kind of nice because like you see like, okay, yeah, it's like pretty periodic. And that's no accident, by the way. So I'm just gonna show real quick. So in my research, I've had to like calculate this by hand a couple times. Oops. Let's see. And if it loads, maybe it won't load. Oh yeah, there it is. Yeah. So and like so ideally, actually the so this is like an example at the bottom here of like the function that comes out of doing this. So it's like, so this energy is just this is like an energy function based on like doing that sandwiching of the wave function and then having our Hamiltonian. And so as you can see, it's all trigonometric. So of course we're going to see waves. So yeah, hopefully that gives some intuitions for why we see these waves and that it's working properly. So yeah, but unfortunately the thing is, so let's look at this. So it's like minimum eigenvalue is like negative 1.8, and then the eigenvalue you get here is like negative 1.36. So not too great, not too bad though either. And so basically, one of the ideas behind this type of ansatz what we're using is that what we can do is actually we can layer it. And so what layering it means is that we have this original, right? So this is like the driver and then the mixer, and then why don't we just add more drivers and more mixers and see how it goes. And so if we add more drivers and more mixers, this is going to do 2 things. It's one, it's going to hopefully give us a better energy value, but 2, and unfortunately for us in the classical world still, and why this like simulation doesn't work very well on a classical computer is because the more you also have way more of these values. So like this is like gamma 0, gamma 1, gamma 2. So you have now 6 parameters that you have to interpolate over to get like a really, really good value. And so that's why we use optimization techniques, because, you know, you're just going to like exploring a 6-dimensional like hyper thing is like very, very costly to a computer. And so that's why we use optimization things. But here, this is still small enough where I can kind of just do it by brute force. So that's what I did. So yeah, this is, by the way, this is the new parameterized wave function. As you can see, it's much, much bigger now. So that's the other unfortunate part of this. But anyways, so the results we got here is like, you know, with 1 round of this, we have like this, and then with 3 rounds of it, we're closer by like a 10,000th maybe. So it's been actually shown that I think like for like these smaller examples, this type of ansatz doesn't work too well, but it works better when we see larger, but of course larger means more costly. Okay. But yeah, regardless, we are still seeing somewhat of an improvement in this. So this is like kind of just to show intuition that like, at least for this type of ansatz, which is made directly from the Hamiltonian, if you add more layers, it's hopefully going to get closer and closer to where you want it to be. Okay. So yeah, but let's move on to like a really big result. Okay, let's go on to the Schrodinger model at like size 6. So like this is like massive already, just the number of terms. And then the ansatz, huge, 6 qubits. And then Hamiltonian doesn't even fit on the screen. This is what I was talking about with the 4096 terms. As you can tell, it's a lot of zeros there. Yeah. Oh yeah, you can. Like for classical computing, yeah, definitely. So yeah. So like it's actually like pretty quick if you do like sci-fi sparse and then like find the eigenvalues here. This is actually pretty fast. Okay. Yeah. But anyways, um, yeah, but that really depends on the Hamiltonian, and of course, like your 6 is still doable, but like once we get to like 20, I'd say that's when a classical computer even just like fails to have enough information to like memory to like take it on stuff. At least my classical machine can't really do 20 qubits. Yeah. Yeah. So this is a Hamiltonian, right? Yeah. It's Hermitian. Yeah. So of course it is indeed symmetric. So yeah. But anyways, let's look at this. So basically we ran our function and we got, and oh, I guess I didn't want to see. Yeah, no. Originally this was showing the wave function, but I guess the wave function was too big to show. But basically, as you can see, what happens here is that like as we increase the size and like increase complexity, the landscape that we get here, which is again just a function of gamma and beta, is very, very rugged. So this isn't as periodic. This is still made of waves clearly, but it's not as periodic as we had seen before. So this is what also makes it like harder and harder for like optimization techniques to go through, because it's like, well, shit, it's not very like any like sort of structure in many places. Okay, and as we increase the number of parameters, it just gets worse. So this is why this method is not very useful on a classical computer. But again, remember, on a quantum computer, we can ostensibly do this calculation very, very, very quickly. And then that's going to be able to give us some values to optimize over. And that's so that's basically the idea here, is that this on a quantum computer is going to be like almost the equivalent of like basically having just a couple of bits, right? But anyways, and maybe some of you who are more actual quantum circuit hardware inclined can like just shoot me down for that, because I don't know my stuff with quantum hardware, unfortunately. But yeah, and then so you can see here that like it also didn't do great, like the real min eigenvalues here, but this one is there. But I want you to notice something. So this is more of like for you guys in like 137B who have taken 137B. Variational quantum eigensolver basically goes exactly on the principle of the variational principle, where it's like any wave function you give it, it is going to have at the lowest the ground state. So basically the idea is that the more the wave function that you give it, we're going to get it closer and closer to the ground state, because we're going to be able to basically get a wave function that is closer and closer to the energy eigenstate of the ground state of your Hamiltonian. Okay. Yeah, that's a lot of words, but if you took 137B, hopefully that was a little helpful to the physical intuition. And yeah, it's just have you taken 137B as well, or do you know the variational principle? Okay, yeah, variational principle. So like there, it's like no matter what wave function you evaluate your Hamiltonian at for your energy expectation, it's going to like at least be, it's going at the lowest it's going to be the ground state, but it's going to be any greater than that, basically. So this is the idea here. You're never going to get, and as you've seen, we're never going to get a ground state that's lower than our real ground state. So at least we have a floor for what to do. And then hopefully, as I said before, when we increase the rounds, we're going to get closer and closer to that ground state. So even if you don't get the ground state this way, you're going to get probably a better floor ground state, like close to ground state, than you had before. Okay, yeah, that's kind of just the idea. Yeah. Anyways, that was it. Yeah. So yeah, remember, just make it Hamiltonians, do some grounds, do some wave function stuff to it, and evaluate the wave energy and pray. So that's how it goes. Yeah. Anyways, thanks. Any questions about anything that was covered? Oh yeah, so I didn't do that here because I was like, well, that's gonna take forever. But instead, like you can think of like the classical optimizer, what it's doing. So like this landscape is actually really computationally complex to like develop. Um, And so the idea here is that like your optimizer, what it's doing is like gradient descent, right? Like you choose some like value and then it's just gonna like test the next value. And it's like, oh, that value is better. Let's keep on going down that way. So yeah, that's like kind of the optimizer. It's I didn't really mention it because the optimizer choice is kind of like it's really up to like what landscape is and what you want to do with it. Wait, sorry, I couldn't hear that. Yeah. So since I basically have like, so basically what I did here is like interpolate over the entire landscape instead of like evaluating just one point at a time. Yeah. This was just for visual purposes. You don't actually do it this way usually because like as we said, we have like a bunch of like we have like n parameters, and you're gonna have like an n dimensional space because of that. You need to use optimization in order to find the stuff, or else you're going to end up like doing like and like some crazy number of interpolation steps. Like I think like for early example, we had like 6, and like that actually was like unironically like 15 to the 6 points that I interpolated over to get a good value. And that was without the optimization. So the optimization kind of just speeds the interpolation up to the point where it's like you're getting a good value, hopefully, without having to take all the points on. Does that make sense? Cool. Uh, yeah, I think so. I mean, like, I think that's like what I was talking about a little over here. It's like we want to get this wave function, right? So, yeah. Oh yeah, yeah. But when we do this wave function, remember, we're like putting more and more of these unitaries on it. So, like, yeah, it's like so. Actually, like that's like you're probably plotting at like probably one of the bigger parts of like actually my research with this, which is like how good can we actually get this value to be? So this is a bit out of scope, but basically there's like an idea that like you can somehow optimize over like these angles like across multiple like you can do a bootstrap it basically. So it's like we were over here, we had so let's go back to here. You can bootstrap this. So it's like this is like this is like 3 rounds, right? So if we find a good value here, we can increase it to 4 rounds and use our like angles that we made here, our beta and gammas here to get another value. And so we really don't know like what is the best, but I think I've talked about this with you before, but we also have barren plateaus, which suck. And this is another example. So this is kind of super out there, but barren plateaus are basically this idea that like the more parameters you have in the circuits, the like flatter your landscape is going to be, and so it's going to be way harder to optimize to find the lowest value of it because of it. And it's like this really weird thing. I honestly don't understand it super well conceptually, but I have for sure encountered it with these simulations before. Yeah, 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 sure, yeah. Yeah, so it's like, yeah, yeah, so that's why like this doesn't work very well for like smaller stuff for some reason. Like it's and also like yeah, just in general, like it's very dubious how some of this stuff works. But it and also we're using a very fairly weak ansatz. So like this ansatz isn't like the best. It's we use it primarily for research purposes to try to find other values, but Qiskit actually I just like ripped this low key this Hamiltonian off of like Qiskit, and like Qiskit had like a different ansatz that was pretty good. So here, let me see if I can. Yeah, yeah you can like use this ansatz here, and then that give that value was actually much better. So this is like, so yeah, your on-dot source, aka the wave function that you're plugging into this, is like super important to try to get good values. This is just one that, like, as it happens, doesn't work so well for small things, but for like things that are larger, it does work better. So any other questions? Yeah, nature's quantum, damn it. You got to make it that way. So yeah, Hilbert space is a big place. You got to make sure that you have a lot of you got to make sure with a quantum computer that you're doing these gates quantumly rather than numerically on a classical computer with matrix multiplication. So, yeah. Just remember, I don't know. I always just remind myself this, like, quantum computers are nothing more than doing matrix multiplication really, 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 really fast. Yeah, exactly. Yeah. And then, like, I guess I know a little bit that, like, the ground states, like, is usually useful for chemical getting chemical reaction, like predicting those functions and things like that. Although I haven't taken PChem, so I don't really know. Any other questions about this? Yeah, cool. Yeah, if not, yeah, thanks. I'll probably send the slides to you guys to post or whatever. And then I guess hopefully the recording turned out well. I did unmute myself. I know that much at least. So, those of you in my decal, I did actually hopefully record with sound this time. I screwed up the first few times I did it and like did not end up using the microphone because I didn't really realize I needed to like use it, but I was like, oh, okay, oops. But anyways, yeah, awesome. So, yes.